This lecture today is going to be an introduction to electrostatics and charges. Essentially, I'm going to be asking you, well, why do things stick together after we rub them together? Well, let's start off with an observation. So if we charge an object by friction, if we rub this balloon on, let's just say, this person's hair, you might say, well, the hair is all kind of static all over the place and the balloon sticks to their head. So when rubbing a balloon against someone's hair, you will see that the hair gets all staticky and the balloon will actually stick to the hair. The hair is all over the place, not because it was messed up, but because it has a static charge. So what is a charge, and how does friction involve static charge? Well, this is where it all begins with our topic on electrostatics. We must begin at the very basic, at the very beginning, that everything is made of atoms. And this is the concept of atomic theory that John Dalton, past historical figure, science figure, said all matter is composed of atoms, elements are composed of one type of atom, compounds contain two or more elements that are bonded together, and atoms do not change their identities. They are just rearranged into different substances. So here's a picture of a helium atom. So we're going to start off starting with the basics. So here's the periodic table of elements, and it's organized in a very particular way. We'll make sense of this as we go. So you are made of atoms. Your clothes and everything in your world is made of atoms. If it is something, it's made of stuff, and those stuffs in their basic form are atoms. Atoms are composed of three subatomic particles. What are these? Well, hopefully you know that they're made up of protons that have a positive charge, right? Subatomic particles and their charges. Protons, positive charge, electrons, negative charge, and neutrons that have zero net charge. So we're going to look at the periodic table. We're going to use this as a reference. We'll get into this a little bit more. Periodic table of elements. We're going to be talking about an atomic number. Helium's atomic number is 2. Its atomic symbol, well, He is helium's atomic symbol. And its atomic mass, and this tiny number in here, but we can see it, we'll get some work with this, is 4.002602. That's helium's atomic mass. So all elements on the periodic table have the name, their atomic number, their symbol, and their atomic mass. And structured, well, let's just say they're going to look very similar. So here's what we can say. Let's start with helium. Helium, the name of the element is helium, atomic number 2, symbol He, and atomic mass. So if we look at helium on the periodic table, it is the name of the element, number 2 is the atomic number, He is the symbol, and 4.0262 is its atomic mass. All elements on the periodic table are written or described this way, just with different numbers as they have different characteristics. So we can start making sense of this. The atomic number is going to give us information. It's going to tell us that it has 2 protons, 2 positively charged protons, and 2 negatively charged electrons. And it also has 2 neutrons that have no charge. And we'll get into how we get to this in just a moment. The nucleus of an atom contains both protons and neutrons, and the electrons can be found orbiting the atom itself. So if we look at helium here, right, the periodic table provides us information. And here's that same concept that we just looked at. When we draw out atomic structures of an atom, we must view the numbers on the periodic table. That the atomic number, right, we said its atomic number is 2. It tells us how many protons and electrons are in the atom. It tells us we have both 2 protons and 2 electrons. These are always equal because all atoms are neutrally charged as they naturally occur. Helium has 2 positively charged objects and 2 negatively charged materials within it. So 2 pluses plus 2 minuses tell me that it has a net charge of 0. The pluses and the minuses cancel out. To find the number of neutrons, one must take the atom's atomic mass minus the atomic number. And we can round the atomic mass to a whole number. We'll get into that here just in a second. So find the number of neutrons. Atomic mass minus the atomic number gives us equals the number of neutrons. So let's do a little practice run. Electron orbital rules here apply. Electrons obey rules as they fill specific regions of space around the nucleus. The first electron shell, or orbital, can only contain 2 electrons. So we'll say the first electron shell or orbital has 2 electrons. The second electron shell or orbital can only contain 8 electrons, which is the same as the third. So second and third can only contain 8 electrons. And the fourth shell or orbital contains 18 electrons. So the word valence, I'm going to use the word valence here very soon. It means outermost. So valence electrons are the electrons in the outermost shell or orbital. And we're only going to go through the first 4 orbitals. We won't go any further from here. So helium has 2 electrons. So here's its atomic structure. In the nucleus, it has 2 protons and 2 neutrons, right? 2 pluses and 2 zero net charged objects. Those are your neutrons. And it has 2 electrons that are in the space around it. These are our electron cloud or electron shell or electron orbital. Kind of all said the same thing. It has 2 electrons in its valence and only shell. So let's do this together. So let's put this all together. Let's do carbon. Carbon is number 6 on the periodic table. Its symbol is C, and its atomic mass is 12.0107. So element number 6 on the periodic table is carbon. It has 6 protons and 6 electrons. Remember, all matter, all elements are naturally occurring, have a 0 net charge. And it has 6 neutrons. I know its atomic mass is 12. I round this to a whole number. 12 minus its atomic number of 6 tells me it has 6 neutrons. So in the picture, you can see that the electron rules apply. Since it only has 2 electrons, it fills the innermost electron shell. But there are 4 electrons that are left, and these 4 spill into the second electron shell. In this case, the 4 electrons are in the valence shell. Because its valence shell or orbital is not full, it does not have 8 total. It wants to react in order to satisfy the electron rule. So it wants to react with another element to become stable. When the valence electrons have satisfied the rule, they are considered stable. Carbon, because it has 4 and it wants to have 8, is very reactive. Carbon is a very good block for reacting on Earth. So here's some more practice on drawing atomic structures. And I give you an example of beryllium, element number 4 on the periodic table, and sodium, element number 11 on the periodic table. And you can try it first on your own. In theory, you could do this along with me as you check out the video here, the screencast itself. But make sure you go back and check. This walks you through it, goes through it a little bit more step by step. However, moving on. So what are atoms made of? Well, historically speaking, J.J. Thomson, a past scientist, thought that the subatomic particles were like raisins in a bun. But this raised a lot of questions. Ernest Rutherford later shot charged particles into gold foil, and most of the charged particles shot through, but some of them bounced back. And the famous phrase came out, "It was as if you fired an artillery shell at a piece of tissue paper, and it came back and hit you in the head." And what happened was, the scientific revolution that was taking place was saying that, well, atoms aren't all space. They're just mostly space. And the reason why you can say that there must be something in there, in this case, the nucleus of atoms, because it had to strike something. Charged particles struck it and reflected back. That positively charged particles would be repelled by the nucleus. So these deflected particles, charged particles, in Ernest Rutherford's experiment started paving the way for atomic theory of saying, here's what atoms look like, and here's what they're made of. So make sure you watch this video. This was loaded prior. So let's go back to subatomic particles and their properties. That we can say electrons have a negative charge. They have next to no mass. They're teeny tiny, very, very significantly low mass particles. But protons and neutrons have tremendous mass. They're about 2,000 times the mass of any single electron. So this is just saying that the mass of a proton or neutron in this case are they're heavier. There's more mass per area. And then here's that cross-section picture I've shown you of helium. Helium has 2 protons, 2 neutrons in the nucleus, and 2 electrons in its electron shell. And here's the key to that. Notice the atomic mass, what I referred to as AMUs, atomic mass units, are really comprised of the protons and the neutrons of the atom. So if you have, in this case, the atomic mass is pretty much 4, because it has 2 protons, 2 neutrons. So it has an atomic mass of roughly 4 AMUs. So what does an atom look like? Well, the idea here is that we're able to put the positively charged protons, the neutrally charged neutrons, and the negatively charged electrons in an orderly sequence that is not only quantifiable, but it's structurally sound. So this is the simplified version of the atom, but it works. We have these electrons in these clouds and these orbitals here. We have the protons and the neutrons in the nucleus. So a helium atom has 2 protons in its nucleus and 2 electrons in the cloud surrounding it. And so that was for helium, and here's for carbon. So carbon, element number 6, has 6 protons, in here, has 6 neutrons in here, has 2 electrons in the first valence shell, in the first electron shell, and has 4 electrons in the valence. Remember, valence means outermost. So the total of 6 electrons are all accounted for here. The 6 electrons are going to counteract the positively charged 6 protons. So a carbon atom has 4 valence electrons. The second energy level is its outermost level, and that's what we can see here. So there's this concept of isotopes, and this is where you make sure you want to take some notes on. So what are isotopes? Atoms and elements are made of protons, neutrons, and electrons. The nucleus is made of protons and neutrons, and the sum of the protons and neutrons is equal to the atomic mass. That's a quick review. In a given element, the number of neutrons can be different from each other, while the number of protons is unchanging. Isotopes are atoms with equal protons, but a different number of neutrons. This also changes the atomic mass units, or AMU, but it does not change the atomic number. So here is an example of a carbon atom, carbon isotopes. Carbon has 3 forms of which it can be found naturally, all of which have an atomic number of 6. They have 6 protons and 6 electrons, but the number of neutrons vary. This is carbon 12, carbon 13, and carbon 14. The only thing different about them is the number of neutrons. In carbon 12, it has 6 neutrons. In carbon 13, 7 neutrons. In carbon 14, 8 neutrons. Well, most carbon atoms have 6 protons and 6 neutrons, right? We can see that when I look at this picture. About 99% of all, the most common form of carbon is carbon 12. But they're not all. Some carbon atoms have 7 or 8 neutrons, and these still have 6 protons and 6 electrons. So it's still carbon, but these varying numbers of neutrons are the carbon isotopes. Stable elements do not decay or break down. Unstable isotopes decay or break down. Carbon 12 and 13 are quite stable. Carbon 14 is radioactive due to an unstable nucleus. Carbon 14 eventually changes itself as it decays into nitrogen 14, and this is called radioactive decay. So here I have carbon 12, carbon 13, and carbon 14. Just one quick summary. Isotopes of atoms of the same elements that have different numbers of neutrons, but the protons are the same. So here I can look at the forces in the universe, and we start putting a lot of big concepts together. We can talk about electromagnetism. That's the force that we're going to be studying in this unit. The force between charged particles. This is what electrostatics is. It involves the forces of charged particles. Opposites are going to want to attract. Like charges are going to repel. We've got the strong nuclear force. This is the strongest force in the universe. It's what keeps the nucleus together. In this case, it keeps protons next to protons. This overcomes the repulsion force of the electromagnetic force. And then we have what's called a weak force. This is a second nuclear force that holds an atom together, which determines the rate that an atom will decay, or if it will decay. So when we look at carbon 14, this is going to be directed by the weak force. Eventually it'll break down and decay. It's called a radioactive isotope. And lastly, gravity. We studied gravity a lot up to this point. This is the weakest of all forces, but it's the only force that works or acts over long or large distances. So when I put it all together and we start looking at what we have going on, we're studying electrostatics. It seems like a long way to get here, but you have to understand where the charges come from. Electrostatics involves forces that are created by unmoving charges. And we need to get some basic rules here. Like charges repel. 2 positively charged objects are going to repel. 2 negatively charged objects will repel. But opposite charges are going to attract. A positive and a negative are going to attract. So if I rub a balloon on my shirt, let's go back to the very beginning. I have moved electrons from one object to another. Both objects were neutrally charged as they naturally occur on Earth. Remember, equal number of protons and electrons. After the friction between the 2 objects, one object lost electrons and the other one gained electrons. That if one lost 5 electrons, that the other object had to gain electrons. And this is a concept of conservation of charge. We'll be reading about this in the near future. So the basic rules, like charges repel, opposites attract. In both scenarios involve forces from charged particles. This is why we learn about the atom or atomic structure while learning about electrostatics. We know that that these objects here, instead of ripping out protons from the nucleus, they gave up electrons, and these are going to repel. Opposites are going to attract, and negatively charged objects are going to repel. And before we get too far ahead of ourselves, I'm going to end with this. I just have a few seconds left. We need to get the concept of Coulomb's law. And if you'll notice, it says the electric force is equal to this constant K times the charge of one particle times the charge of another particle at some distance squared. If you notice this is similar to the universal law of gravitation, it is, and the same relationships apply.